Welcome back, Chemistry Theory. This is the second section in the new EQ acids and base equilibrium unit. So this is 3.2 Bronsted-Lowry acids and bases. So we'll understand the nature of the hydrated proton, represented as either H plus or H3O plus, and define and identify Bronsted-Lowry acids and bases, and identify conjugate acid-base pairs. So the previous section we looked at their Arrhenius definition, one in which has an acid being something that dissociates or breaks down and releases H plus ions, and a base is something that dissociates or breaks down and releases OH minus ions. So in 1923, the Danish chemist Johannes Bronsted and the English chemist Thomas Lowry independently proposed a more general definition of acids and bases. Their concept is based on the fact that acid-base reactions just simply look at it in terms of what has happening to the H plus ion. So kind of doing away with the OH minus ion being that of a base, just simply take a look at what the H plus ion is doing. So the H plus ion in water, the ionization of HCl in water produces hydrogen ions and chloride ions floating around the solution. A hydrogen ion is no more than a bare proton and interacts strongly with non-bonded electron pairs, such as the electrons on the oxygen atoms of the water molecule. So if you imagine a Bohr diagram of a hydrogen atom, okay, so we have one proton in the nucleus, one electron in the outer level. If that electron was to disappear, we would just simply be left with bare proton in the nucleus. And that is what an H plus ion is. Something that has lost an electron and is just simply an H plus ion. It's attracted closely to the, remember, water molecules are negative in the oxygen area and positive in the hydrogen area. So we have this positive attracted to the negative area and it attaches like that. Overall, this positive charge of the hydrogen is spread throughout the entire H3O ion. So this is a H3O ion, which is referred to as the hydronium ion. So H positives floating around the solution are synonymous to an hydronium ion. So chemists use the notation H plus or H3O plus interchangeably to represent a hydrated proton responsible for characteristics of acids. So the H plus ion and the H3O plus ion are identical. They're used interchangeably, illustrating something that has an overall positive one charge. So we often just refer to it usually as the H plus ion, even though in reality it's more like an H3O plus, because H plus ions quickly attach to water molecules to make the hydronium ion. So sometimes it's referred to as a hydronium ion, sometimes it's an H plus ion, or sometimes it's just simply referred to as a proton, because that's what an H plus ion is. It's just simply the nucleus left with a positive charge in the middle. So when the reaction occurs with HCl dissolves in water, the HCl molecule transfers an H plus ion or a proton to a water molecule. Thus we can represent the reaction as occurring between an HCl molecule and water molecule to form the hydronium and chloride ions, as seen on the next page. So if you look here, we see the HCl combined with water, and of course the H plus is going to go and attach itself to the water molecule to make the H3O plus ion, the hydronium ion, and that'll be left with chloride with an overall charge of -1. And here we can see the Lewis structures of all of those. So the substance that gives up the H plus ion, the hydrochloric acid, is the acid, and the H2O, which is receiving the H plus to make the hydronium ion, is referred to as the base. So the polar H2O molecule promotes the ionization of acids in water solution by accepting the proton to form H3O plus. Therefore, Bronsted-Lowry proposed definitions of acids and bases in terms of the ability to transfer H plus ions. So they said that an acid is something that donates. So it's like over here, it donated, it released the H to another substance, and a base is something that accepts the H plus ion. So over here we could see that Well, this is the acid because it gave up the H, and then the H went to the water molecule, so that's acting like a base because it accepted it. Quite often we talk about this in terms of a foot bag analogy or a hacky sack from back in the day analogy. So if we have someone that's kicking a foot bag to someone else, the one that's donating it is the acid, and the one that's on the receiving end of it is the base. Okay, so we can kind of think of it like that. When HCl dissolves in water, as seen earlier, HCl acts as the Bronsted-Lowry acid, and the H2O acted as the Bronsted-Lowry base because it accepted. So base accepts, acid donates, or gives up. Another example occurs between HCl and NH3 when an H plus is transferred to an acid. So if we look over here, HCl becomes Cl. So we can see that it must have donated an H. Donated H. And then NH3 became NH4 plus. So it accepted an H plus. Because what really happened here is that this H went over there. And if we compare the before and after substances, we can figure out what happened. So HCl became Cl, which means it released its H. It donated an H. So it's referred to as an acid because it donated an H. NH3 became NH4 plus. We can see that it accepted an H because that H from the HCl went like this, and it attracted it. Another example occurs with the aqueous solutions of ammonia, in which we have this equilibrium. And again, we can take a look at what's happening here. NH3 becomes NH4. So we can see that it accepted an H, and H2O became OH. So we can see what happens before and after. It lost an H, or we could say it donated an H+. So of course, what happened here is that one of these H's went to here. We can compare before and after to see what happens. It's either gaining an H or losing an H, so that helps us identify if it accepts an H, it's a base. If it lost an H or donated, it's an acid. And of course that H that was donated and accepted is right here. So ammonia is a Bronsted-Lowry base because it accepts the H plus from H2O. Water is a Bronsted-Lowry acid because it gave up the H to NH3. An acid and a base always work together to transfer an H plus ion. In other words, a substance can function as an acid only if another substance simultaneously behaves like a base. So if you give up something, you have to receive it. It's like a transfer of money or a transfer of the hacky sack or foot bag like I talked about. To be a Bronsted-Lowry acid, a molecular ion must have a hydrogen atom to lose as an H plus. To be a Bronsted-Lowry base, a molecular ion must have a non-bonding pair of electrons. It's those non-bonding pairs of electrons that attract that H. In the Ford reaction of this equilibrium, which is the Bronsted-Lowry acid and which is the Bronsted-Lowry base? So of course it involves us simply looking at a substance. Now, we're going from left to right. Look at a substance that has either gained or lost a single H. So H2S is closely related to HS minus. So we can see we would pair those up because they only differ by an H. And of course, to go from H2S to HS, we lost an H, or the terminology used is donated an H plus. Then if we look over here, going from CH3, NH2 to CH3, NH3, you can see it accepted an H. And anything that donated an H is called an acid. And anything that accepted an H is called the base. And for all this to happen, of course, it's in reality this H here, one of these H's goes from here to here. So if we look at what I like to call is the BL acid, or the Bronsted-Lowry acid, is H2S. And then the Bronsted-Lowry base is the CH3NH2. Okay, so that's how that works. Some substances can act as an acid in one reaction as a base in another. For example, H2O is a Bronsted-Lowry Bronsted-Lowry base in some examples, and a Bronsted-Lowry acid in other examples. A substance that is capable of acting as either one is called amphiprotic. An amphiprotic substance acts as a base when combined with something more strongly acidic than itself, and as an acid when combined with something more strongly basic than itself. Okay, I think we'll stop the video right there. Part 2, we'll look at conjugate acid-base pairs.